Okay, so today we talk about exploratory analysis. We call it exploratory analysis, but it's actually unsupervised machine learning. We apply some, clustering program algorithm to look at the data, try to identify structures in the data, and also visualize them. For high throughput data analysis, all this exploratory data analysis will lead to some visualization of the data, and so that we can see if there's any biological experimental parameters. Say if we have cancer versus healthy control, we would want to see a relatively clear separation of the two groups by visualizing the data, right? And also we could identify any outliers or influential cases by doing exploratory analysis. And we can also find groups of genes or samples sharing the similarity. So when we talk about unsupervised learning, that means this analysis makes no use of any grouping of the samples with any gene annotation. So we just pretend we don't know anything about this. We just, throw in the data and let the algorithm run and see whether we see any patterns in the data. Okay. But this is called unsupervised because there's no grouping information guiding the algorithm to go. It's purely based on the data itself. Okay. And one of the exploratory analysis will be doing clustering. This is when you have n unlabeled samples, and we want to group these n unlabeled samples into k partitions, k groups. Okay, and the only information the clustering algorithm needs is the similarity, or we call it dissimilarity. They are the same thing, just how similar or how different they are between the samples. And a clustering algorithm, it groups samples based on their mutual similarities. And a good clustering algorithm should achieve two things. One is high within cluster similarity, and another one is low inter-cluster similarity. So we want everything within the same cluster, they are as similar as possible, right? But we want the two distinct clusters, they should be very different. But this is like a trade-off. So it is a trade-off between these two things. So this is just a simple demonstration. If we have, suppose we have a two-dimensional space, and we kind of have all these, each dot represent one sample. You can think of this. And initially, we visualize the samples like this. After applying some clustering algorithm, we could identify two groups, two clusters, the red cluster and the green cluster. But this does not necessarily correspond to the actual grouping of your samples. It's just based on the data itself. So if we want to cluster gene expression data, we can do it both ways. One would be we can apply clustering to the rows. Remember the gene expression matrix, the rows are genes and the columns are samples. So we can apply the clustering algorithm to rows of genes and also to the columns of the sample, depending on what you want. Okay. If you want to separate the groups of sample, like from healthy control to cancer, then we apply to the columns. But if we want to cluster the genes to find out a set of co-regulated genes, then we apply to the rows of the gene. And also, by doing clustering, we will allow the reordering of the rows or columns of the expression data matrix. Then it will be easier for visualization. For example, by looking at that's the heat map. This is after we do some clusterings and rescaling of the data. So like I said before, if we cluster array samples, we can detect experimental artifact or bad hybridization. This is also like a complementary step for quality control. We can check whether samples are grouped according to known categories. We can also identify new classes of biological samples. By clustering genes, we could identify groups of co-regulated genes. And these clustering genes is the main idea of the WGCNA, the weighted gene expression, co-expression network analysis. What they perform would be to cluster a set of genes and to identify several modules and then try to correlate these modules with external traits. Okay. So what I talk about today is more of a more general way of doing it, not the WGCNA. There will be one lecture specifically for this topic. So the thing, like I said, the clustering is to group the samples using to see how similar they are, using how make them as similar as possible. So the first thing we need to define a similarity measure, and here we call this as distance measures. Okay, and the result of the so depending on how you choose the distance measures, your cluster results will be very different. And I will show you an example later. So here are a few very common distance measures. So some mathematical representation, if you think X and Y will be array samples. So two array samples, one is X, one is Y, okay? And each one comes with like n gene expression value. You can think it's n1 to n as you have n genes for sample X and n genes for sample Y. And then this Euclidean distance, this is the most common one. It's defined as is like the square, the sum of the square root of the sum of the square distance between the two samples. Yeah. And then another one is called the Manhattan distance. This is essentially like the absolute, you add up all the horizontal and vertical distance between, the absolute distance between the 2 points. It's called Manhattan distance because it's like the street map of Manhattan, New York. Is like the grid. So you're adding up all these vertical line and horizontal line, and you get the distance. And another one will be 1 minus Pearson correlation, because this is essentially like a dissimilarity measure. For similarity measure will be the correlation, but because it's dissimilarity, so you use 1 minus it. And this is like the mathematical expression for calculating Pearson correlation. And this is 1 minus. Okay. And you can actually, you can do Spearman correlation as well. There are so many distance measures. But these 3 are the most common ones. And next I will talk about one very simple basic clustering algorithm that is called the k-means clustering. So the k-mean clustering is very simple and intuitive. So imagine you have several points here. Each dot represents 1 sample, and initially we don't know. We just treat it as one big bulk of dots. And then first thing will be we kind of like randomly pick. So for example, if we hypothesize this will be separated into 2 groups. this is one thing you need for doing k-mean clustering. You need to predefine how many partitions you want to divide the data point into. Okay, now if we want 2 clusters, and we kind of randomly find the starting point for these 2 clusters, and this will be the starting point. And then from the starting point here, for each of the starting point, we calculate the distance of this point to every single data point. Okay, so for the blue one, I should put here, for the blue, so this is like every single point we calculate this. And for the red starting point, we also calculate the distance. And then we pick the smallest one. For the same data point, we pick the smallest distance between these 2 distance to the starting point. And then the one that is smallest will be grouped to the corresponding color. Mm-hmm. So this comes with the first partition. Okay, so the red dots will be they are partitioning to the red cluster, and the blue points belong to the blue cluster. But this is just the first step, but this is like an iterative process. And the second step, once we have the first grouping, we need to recalculate the center of the cluster. So we will no longer use this starting point. The starting point for the second step will be the average distance of this blue cluster, which will be here. And for the red cluster will be the average of all these red dots, and it will be repositioned here. Mm-hmm. Okay, and then we start the second step of clustering. We will similarly calculate all these dots to the red cluster center. At the same time, also all these the blue dot we calculate to the red cluster center. Again, we get all this distance calculate, and similarly for the blue cluster center, we calculate all the distance, and we pick the smallest distance between the 2, and then regroup the data point, and we color them. Mm-hmm. And then the third step, again, recalculate the cluster center based on the new partition. And this step, goes on and on and on. As you can see, the shape kind of like change as time goes by. And we stop this algorithm when the center stop moving. Of course, it will not stop moving absolutely, but you can set a threshold for the, how small it moves. If it falls within that threshold, you just stop the algorithm. Or if it goes on forever, you can set, I want to stop after 100 iterations and things like that.
So it doesn't matter the 2 starting point.
It matters.
It does matter.
Yeah, it does matter.
But then, how do you choose them?
So the next slide say so the issue with k-mean clustering is extremely sensitive to the cluster center initialization. Okay. So bad initialization can lead to poor convergence speed, right? It will go on for thousands of rounds and it will not converge, or it could lead to bad overall clustering. If the shape of the data is irregular, kind of convex, and then you will not get a good result. And there are several solutions. One will be like many iteration algorithm. The initial value usually will pick one of the sample as the first center. Okay, and the second will be the farthest from the first, and third will be the farthest from both if you have k more than 2, and so on. So this selection will kind of first to pinpoint your first center, and then make sure the rest will not goes too far away. So the first procedure, you pick the first center as one of the example, and the second will be the farthest example from the
center
first.
For the whole.
Yeah, to make sure you have the whole data set covered this way.
So the first one is like a mean of the data, kind of like that?
One of the example.
Randomly choose one.
Yeah, we randomly pick one, yeah. And another way would be you actually try multiple initialization and choose the best results. And the third one is it's called a K-means plus algorithm. And this focuses on a smarter initialization. It's basically based on some distribution probability of the similarity measures. If you're interested, you can read about it. So basically, there are ways to do a smart initialization to avoid these issues. Okay? All these software program would have a specification and let you specify how you would like to initialize. But usually, if your data looks like regular data, is nothing very odd, you just use the default setting and it should be fine. Or you can try multiple initialization if it does not take a long time to run.
So we have to set the seed because otherwise, every time you run your program, you end up with a different.
Yeah, you also need to set the seed. What is the seed?
Like set the seed for the program because otherwise, every time choose a random different.
Oh, the seed. Yes, of course. Yeah, always set a seed so that you can reproduce and trace the results. And another issue with the K-mean clustering, we need to specify the number of clusters. One way to select the K would be to try different values of K, and then we can plot these. I call this the elbow plot. Because, like I said, a good clustering algorithm, you would want the within cluster, they're similar. That means the error will be small, right? The within cluster variation will be small. So we can calculate the sum of the square error, which will be the within cluster variation. So for a different K, we can calculate this value, and we can plot this within cluster variation over the number of Ks. And the one, we look at the elbow point, kind of like when that's the point when your error versus your K kind of get plateau. Then we pick this point. The corresponding K will be the number to pick. Okay. Any questions?
Your sum of squared error is the sum of the distance between each sample to that sample for the center that sample was assigned to.
The within cluster variation. Yeah, it's basically the
each cluster.
It's a distance. It's basically Euclidean distance.
Yeah, distance.
Yeah, it's the sum over all the pairwise Euclidean distance. And K-mean clusters usually works well, but for some situation it doesn't. If your data looks like this, like a non-convex, non-round shaped clusters, and K-mean clustering will not be able to do well. Okay, if the two groups should look like this after K-mean clustering, it might look like this. And also, if your data have different densities, K-mean clustering algorithm will get confused. And if this is true after K-mean clustering, it will look like this. All right, so this is the basic K-mean clustering. So the K-mean clustering is very simple, and it has been there for many, many years, but it's very useful. I think it can essentially pattern type of data. K-mean clustering. And the next one, the hierarchical clustering. This one is useful for the specific type of data we will be analyzing. So hierarchical clustering is not like a K-mean clustering. It produces a tree, or we call it dendrogram. Okay? The good thing about hierarchical clustering, we don't need to specify K. So we don't need to tell the algorithm how many clusters we want. The number of clusters we obtain depending on at which point at the branch we cut the tree, then we will end up with how many clusters. Okay. And the tree building can be done in two different ways. One is the bottom up, and this is called the agglomerative clustering. And the other one is top down. This is called the divisive clustering. And we'll focus on this bottom up agglomerative clustering. This is more common. So the bottom up algorithm start with n clusters. So basically you think it starts with n data points. And then at each step, we merge the two closest data point or clusters once you get small cluster. And then use a measure of between cluster distance. So now, for k-mean clustering, we only have a distance measure between two samples, right? Well, between the sample point and the center. But for the hierarchical clustering, now we have two distance measures. One is between sample distance, and the other one will be between cluster distance. Okay. And the between cluster distance, there is another fancy name for this between cluster distance. We call it linkage. Okay, so it's a different rule of defining the distance between two clusters. One is the single linkage. This is also called the nearest neighbor linkage. The distance between the two clusters is the minimal distance between the two objects, one from each cluster. And another one, the average linkage. This is the most common one. It's the distance between the two clusters is the average of the pairwise distance between members of the two clusters. The third one is called complete linkage. And this is the distance between the two clusters, the maximum of the distance between two objects. And the last one is called the central linkage. That would be the distance between their central of the two clusters. Would be the distance between the two clusters. Okay. This is simple example like if this is single. So suppose we have two clusters, the blue and the red cluster. The single linkage will be the closest, the nearest neighbor. This will be how you define the distance between the two clusters. Okay. But remember, this is just define the minimum distance. But for the distance, it also comes with the different definition. We have the Euclidean distance, we have the Manhattan distance, we can have 1 minus the Pearson correlation. Okay. So this is in terms of you actually calculate the distance, you have those measures, and this is how you define, the distance between the two clusters. Is that clear? Okay. And then for the average linkage, this will be you calculate all this distance, the pairwise distance, and you pick the average of this, and the distance between these two will be the distance between the two clusters. Okay, and the complete linkage will be the maximum between the 2 points, and the central will be you calculate the center first. And then the distance between them. So that the average and the central distance, they are different. The linkage, they are different. Okay.
The average of
one is calculate all the pairwise distance and then get the average. And the other one is calculate the average first and then get the distance.
The only thing I don't understand is the average one, the two. The two center, what are they? Because they're those are the two crosses.
Those are averages. I think the red one is the average of distance from.
No, the average is.
I think it should be. Let's see. The distance between is the average between the member of the two.
There shouldn't be.
This dot is just it shouldn't be
Shouldn't be
cross.
across there, right?
It shouldn't be across.
Yeah.
The distance should be one of these
Yeah.
pairwise distance.
Uh-huh.
Yes, you're right.
Okay.
So this cross are not really there. This cross is just try kind of like to demonstrate
the
this is at the
center.
center of the.
Yeah,
The last one is useful for having a cross, but not the first three.
How do you define the center for each cluster?
The center?
Yeah, how do you define the center for each cluster?
For this one, you don't need to define a center for each cluster.
Isn't it the average of the distance?
Unless you want the centroid, using a centroid linkage, then you kind of like define it.
Is the average distance within the cluster?
Yeah.
Like whatever you define your distance, the
then
average
that
of
would be the
distance.
centroid. You only need to find a centroid if you want to use centroid linkage method.
Yeah, how do you calculate the centroid?
It would be the average.
Yeah, of those.
Like all the pairwise within the same cluster, then you get a center here. So it's like the k-mean clustering. When you calculate a new center, when you find a new center, will be you calculate this red color, all the pairwise distance, and then the middle point will be the new centroid.
The distance add up to be 0, kind of.
No, they don't.
No, the center.
Oh, with the center.
Yeah. Like
Distance between whale and whale, between each
Because
all pairwise.
all pairwise.
no, between the center and each one
All
should
pairwise.
all add up to 0, because that's the center.
No, distance is always positive.
Well, yeah, but yeah, you're right.
Yeah. All is all pairwise distance, whatever we define the distance, then we get all pairwise distance within the cluster, and that's and then you average it.
But that's only the average distance. But how do you the coordinator of the centroid? How do you calculate that? I guess my question is.
It's
Oh,
I guess it's then it's the minimum. Like
Do we do
make all
the
the distance
distances?
minimum.
I
adding
think
up
it
would
just
be
should be the meaning,
Well,
the
right.
location
Anyway,
that
it's the center.
yields
Think
the
about it.
smallest sum of
The package
square,
will
something like
will
that.
get it for you. I think the package will calculate for you.
She says you have this,
But the
this,
concept
but
is
then
just
she
find
says how you
a
get an
center
X
of.
and a Y. Because if you're looking at the distance,
那
it's
你有
only
一
one
堆东西，
number.
当然要有
Right,
个
it's like
center。
是啊，是
two.
要有个 center，就是它的
Three.
这个 center
So
的
add this up is a number like 5,
大概其
but
概
doesn't
念
have
有了就
coordinate.
行，别管它怎么说。
So how we get coordinate? What I'm thinking is each one of them have an X maybe, and then we calculate X average
it's a
and Y
two-dimensional,
average. Yeah.
Oh, yeah, average of the like you have
That's
to
the
have.
question. Like from if we only get distance, we only have one number, and one number adds to one dimension. However, this has 2 dimension. So how do we come up with a center
Yes.
that has a 2
Yes,
dimension?
that's my question.
Yes.
Oh, you want the dimension wise, yeah. Then the average. Then you basically find a starting point, and then you can get the 像个坐标一样找个原点，然后
If
那
you
个
want to get the coordinate of it,
then you get an average of the x and average
it's
of y.
basically it's not like you can get a coordinate for it right away. I think that
Yes.
You have
it
to
also depends on how you define a centroid. I mean, it's the between the centroid. The centroid, it depending on how you define the how should I put it?
I don't think it depends. It's
How
just
about if you're looking at that as X and Y, and this
Yeah,
is
if you
the
look
square
at
root
your-
of X plus
your-
Y squared, and
That's
each
the-
one of them has
yeah, well,
that.
you need some criteria for defining your centroid. If you
Yeah.
want the centroid is the one that yields the minimum, well,
And
yeah,
then-
minimum.
like a minimum sum of distance
yeah,
of to
Of
all your
all the-
data point within the same
or the
cluster,
cluster,
then that one will be
the
your
center.
defined centroid.
I'm thinking,
But if you want the one will be sort of like the average of the sum of, well, could it be one?
No, that
Should
should
be the
be
minimum.
minimum. Yeah,
Should be
that's
the
what
minimum.
I was
Then
talking
you
about.
one common way should be the minimum.
Yeah.
This can be, I think the coordinate would come like this. This is X and Y.
Yeah.
This is another
Oh,
point.
no. Adding up
if you
should
look at
be
the
the minimum.
coordinate, the average of this is
Adding
here.
if you find the point which all
Yes.
the dots in the cluster to that
Because if you
center, adding
one
up the
here,
distance, adding up should be
here,
minimum.
Yes.
The center of this point is here and has an X.
It really depends on how you calculate it. You can just think it as the simplest way. You have only 2 data points, and your central will line in the middle part of that line. Right?
Yeah, in the middle.
And then if you introduce another data point, then you
the
can.
triangle is
Yeah. So you think about it as just starting from 2 data points, and then you add 1 data point at a time, and you can get the center point.
Yeah.
Every step, and then you kind of end up the last one would be your central. If you want to define it this way, you start with 2 data points and you draw a line. Once the central will be in the middle of that line, and you add another data point, the central will be this data point with the new data point, the line, and the middle of that.
Yeah.
I mean, it is just depending on how you define it.
Okay.
I really don't know the actual algorithm of doing the calculation.
The triangle
here.
But I think it's also an iterative procedure. It's not like one step you can get a central.
geometric center.
But there are of course clever way of doing it, but this could be one way.
Yeah, there are different ways you can actually come up with
Yeah.
this.
But that way, it also
With the
probably
minimum-
depends on which one you get in the third and like the.
But you always
order
depend on what kind
getting
of distance measure you use, you know.
I was always thinking of like doing them all together. I don't
Okay.
know. Sorry.
Okay, so yeah, I'll get back to you on how the central is calculated next time. I'll look into it. All right, so the actual hierarchical clustering algorithm, the steps involved. The first step will be to compute matrix of pairwise distance. And then the second step, we find pair with minimal distance and merge them using one of the linkage rule. And after that, we will update the distance measure matrix. And then we continue with not really step 3, like the previous 3 steps until a single cluster is formed. Okay. And the parameters we need for doing this, one is the distance measure for individual samples, and the other one is the distance measure for clusters of samples. That's the linkage rule. Then recall this is the distance measure between individual samples. Okay, and here is the one simple demonstration for how hierarchical clustering is performed. So here we will produce a tree, and the y-axis, the height of the tree, is actually the value of the distance matrix between the clusters. And then in this example, we will use average linkage rule. Okay. All right. Now imagine we have 5 data points, and then in a 2-dimensional space. So we can so each data point will come with x and y coordinates, right? And if we use, say, if this is, I would say, Manhattan distance, just think of as the absolute value distance, and then we can calculate each pairwise distance of these 5 data points and construct a distance matrix, right? So you can think of all these diagonal values will be the distance of that data point to itself. Now, of course, it's 0. And then the off diagonal one, say if this is 1 and 2, that means that's the distance between data point 1 and data point 2. So this is 2. And 1 and 3 here, the 6th will be the distance between 1 and 3. And 1 and 4 will be distance 9. Well, it's not actually accurately scaled, but just think of it like this. And then 1 to 5 will be this. Okay, so the 4 should be here. anyway, and so on, and you construct this distance matrix. And then now we look at this matrix and we pick the smallest distance, pairwise distance, because the algorithm said find a pair with minimal distance. And then we merge them using one of the linkage rule, okay? And now we use the average linkage rule. So this will be the pair with the smallest distance, and then we merge these 2 points together. Okay? And now we got this one cluster here, and then, okay, the next step, we need to update the new distance matrix. And now we no longer have data point 1 and 2. Now we have a new cluster called U. And we calculate the distance of this cluster to each individual point. Okay? And this 5.5 comes from, I think the 5.5 comes from, okay, this is 5 and 6.
Yeah, that's 5.
Yeah, the average linkage. So this comes from, why is the average linkage? Because point 1 to 3, the distance is 6. 2 to 3 is 5. So they have the average is 5.5. Okay, and we update this distance.
So basically, it's a 3 to the middle of 1 and 2.
Well, not really the middle. It's the average.
Okay.
It's not the central. It's the average.
Okay.
And then, but the distance, like the U to 4 is still the same. You know, like not the same, but this is kind of like calculate the new distance. I think it's changed. Yes, this is the average. 9 plus 7 is 16, so divided by 2, so you get 8, and so on. Okay. And now in this updated matrix, we look at the smallest pair of distance. That would be between data point 5 and 4. So that's 3. Okay. Oh, I forgot to mention, once we form one cluster, we plot it here over the dendrogram and make it here. And the height of this actually represent the distance matrix between the two data points. So that would be the 2, right? Yeah, that's 2. You just imagine that's 2. Okay. And then now we have 4 and 5. They form another cluster. And now we have this. And again, we update the distance matrix. Now we have 2 clusters, U and V, and a single point, data point 3. And again, we perform the same thing, you know, using average linkage and Manhattan distance, and we can get all this value. And the next one, we see the smallest pairwise distance between data point 3 and cluster V. And at the same time, we also plot the 4 and 5 here. And the height will be their distance.
3.
3. Is that 3?
3.
Yeah, 3. Well, it looks more than 3.
Well, it looks like at least 4.
Imagine it's 3. Yeah, I should change that matrix, make it more convincing. I think I kind of eyeball the distance and put those numbers in back then. Anyway.
The 4 should be farther away somewhere.
Yeah. Okay, so now we merge data point 3 with the cluster 4. So this is different from k-mean clustering, you see? It's not like, it's not trying to separate the cluster. Actually, one cluster can, you know, nest within a larger
It's
cluster.
a tree.
Yes. So it's not a linear relationship anymore, right? So it's more usable. You don't need a linear. It can handle non-convex problem. So this now we end up with 2 cluster U, and we rename this like a W. And then we can plot this data point 3, and together with this cluster V formed by 4 and 5, and things like that. Okay. And the last step will be just, forming one big cluster. And this will be the final, tree branch. And this is one tree. And then depending on how many K you want, partition you want, we usually, like here, we will perform tree cutting. So if you don't cut the tree, you will have one cluster. That's the final product of doing hierarchical clustering. But we always want some, separation of the data. Then you do the tree cutting. And depending if you want to cut tree here, we'll have 2 clusters. If you cut the tree here, we'll have 3 clusters. And if you cut the tree here, we'll have 4 clusters. And if you cut the tree, at the very bottom, we'll have 5 clusters.
Another question. So each, the clusters, is it going to be always 2 or it could be like a lot?
Always
like a
2.
small.
You will have many. Yeah, you have many. Yeah.
It's just an example showing.
But eventually it's always you get 2 data points. The end it's like, I would say the leaves. You always get like 2.
Yeah, 2 from
not always. Like here you get only 1 leaf, right? But it's always like a 2. Yeah, merged together and so on. But it's like every single step
the second step could be 2 adding in.
Mm-hmm.
But this first step always has to be
it's
not necessarily. If you have 3 data points, the distance between
it's the same thing that the 3 will get together.
Yeah, not necessarily.
So say if the matrix
can be more than
more than 2. If you get 2 here, then you get 3 points merged together.
I get it.
But it's kind of rare. You don't always get exactly the same number, right?
Yeah,
unless you round all your distance into integers, so then you might end up with the same.
It's possible, but in reality, you might not see this.
Yeah. So this is one of the actual example of doing hierarchical clustering. This is a very famous leukemia data set. So they have 150 genes. How many samples? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. About 30 samples of ALL and AML. And after clustering, it looks like this.
Wow.
I mean, it
doesn't
really show a very clear separation. Well, it does.
It does.
I think, the AML is former. But this is kind of expected. Why? Because this is based on 115 genes, and they're already differentially expressed. So you would expect, based on this set of genes, there should be a clear separation of sample. And I wouldn't say this is exploratory analysis. This is more of like a confirmatory or visualization of your candidate gene list on your data.
This is highly differentially expressed genes between AML and ALL. This is with the highest variance across all samples, but still get this perfect separation.
Yeah, and also you can see kind of even within the ALL samples, there are 2 clusters, right? There's 1 cluster here and 1 cluster here. You might want to look at this sample to see if there's some distinctive characteristic of the patient that could lead to this separation. Okay. And again, this y-axis, based on the value here, I would say they use some kind of distance measure, not correlation, not based on correlation. They just use the Manhattan or Euclidean distance and things like that. That's usual. I mean, if you want to cluster the genes, then you usually use correlation. But if you want to cluster samples, you will use all those usual distance measures. Okay. So next, I will talk about what distance measure to use. Okay, it really depends on your goal. If you're trying to differentiate sample based on the gene expression values, use distance measures like Euclidean distance or Manhattan distance will give you more sensible results. Why? I will show you why, okay? And the second, if you want to identify state of co-regulated gene, then using measures like 1- correlation will be more suitable. So this is a simple numerical example. Imagine we have a matrix 4 by 4, okay? And the rows are genes. So say we have gene 1, gene 2, gene 3, and gene 4. And the column, there are samples. Just imagine this is sample 1, sample 2, sample 3, and sample 4. Okay? And if we look at gene 1, the expression profile, you see this 11, 13, 15, 17, it keeps going up, like an increasing trend. And for gene 2, we see an up, down, or it should be down, up, anyway, like this zigzag pattern. And for gene 3, again, we see an increasing trend, but a smaller, lower expressed as compared to gene 1, right? And then for gene 4, again, we see this zigzag pattern going up, down, but also low expressed as compared to gene 2. So if we think, if we are trying to see, if we use Euclidean distance, the smallest distance will be between x1 and x2, right? Because they are kind of like similarly expressed. They are all highly expressed genes. X3, X4 will fall into the same category as lowly expressed genes. Okay? Mm-hmm. But if we use correlation to look at these 4 vectors, the smallest distance will be between gene 1 and gene 3 because they're all going up. So they show the same trend. And also between X2 and X4 because they also show that up, down pattern. Okay, so it really depends. So if we, so that's why, depending on what you want to do. If we do apply this hierarchical clustering algorithm using 1- correlation, like I said, X1, X3 will cluster together, and X2, X4 will cluster together. And the height of our tree will be the 1- correlation. Okay, so you see the largest will be 2, 1. And if we use Euclidean distance, gene 1 and 2 will cluster together, 3 and 4 will cluster together, and the height will be the distance. Okay. So if X1, X3, X2, X3, X4, they are individual samples representing, cancer versus healthy, then by clustering, we'll expect to see X1, X2 be together, right? But X3, X4 will be another cluster. So using Euclidean distance will help. So if this is like looking at the matrix another way, transforming it. But if, like I said from the very beginning, if these 4 are genes, then by using the correlation, we'll be able to see the way it behaves, the pattern. That means how they co-regulate together. Any questions? So basically, the take-home message is if you want to cluster samples, you use Manhattan or Euclidean distance. If you want to cluster genes, use correlation type of distance matrix measures. And that will help you identify the pattern. Any questions?
So if the expression of the gene is correlated with the biological kind of characteristic of the sample, how would it show itself up? in the correlation, when we get the correlation, with like among genes. Like for example, if we have like these 4 genes, and one of them is cancer, the other one is, for example, healthy, and the cancer one are highly expressed one. So when we say cancer and no cancer, we're actually dividing patients, right? It's not.
Yeah, so then it will be the first case. So if you think the gene will be highly expressed in the cancer sample, then you will want to find those highly expressed.
It would be Euclidean distance or some sort of distance. So
then once you identify this set of highly expressed gene, you want to see within this set of gene, there might be some of them, they will behave the same way. Then you will probably further step would be using the correlation.
That makes sense.
Yeah. All right, next will be heat map. So this is a graphical representation of data where individual values contained in a matrix are represented in colors. But the values in the heat map should somehow be standardized. So one common choice is to make them into the z-score. So this is kind of like a normalized, well, not the normalization we talk about for the pre-processing. It's just 1 minus their standard deviation and then divided by the, 1 minus the average and divided by the standard deviation. Okay, that way we can kind of rescale all the value, and so the color, the temperature of the heat map will not be that drastic after you standardize the value. Okay. And also, if you want to show difference between samples, we should plot z-score by centering and normalizing the expression value of each gene across samples. Let's see, across each gene across sample. I think that's what I usually do, because the heat map usually I just want to show the group separation, like based on the gene expression profile. Yeah. But if you want to show correlated gene, you should plot z-score by centering and normalizing using the value of each samples across genes. So this is like an example of heat map. So basically, this one, this already scaled like a normalized. And again, the rows are genes. Rows are gene, and all these columns they are biological samples. And as you can see, the coloring scheme, you can specify coloring scheme when you plot the heat map. So here, the red color, actually the warm color, the red color corresponds to negative score. So this is like a low express color. And then this is like the green color is 4, corresponds to a positive value. And on each axis, like here, there's the dendrogram. This is like clustering the samples. Okay, they perform hierarchical clustering for the samples. And the y-axis here is another dendrogram. They cluster the genes and create this dendrogram. And here is the list of the genes. And here is the labels of the samples.
Interesting.
In R, you can create this by just 1 line of code. But with many different choice of the specification. Whether you want to do clustering on the y-axis, or both, or none, or linkage method, similarity measure, all kind of things. Wow. So it's very handy.
So these are row normalized z-score, right? These z-score are row normalized because they said in the figure it said row z-score. They mentioned.
I believe it's they normalized with respect to the row, across row,
Yes.
because they want to separate the samples. And after that, they kind of rearrange the, not rearrange, it's all based on the clustering algorithm. Also, the set of genes that behaved similar, they got clustered together. So that's why you see the blocks of color. Yes, otherwise it won't be a block of color. It will be, you might see clear separation from the left to the right, but probably not the block of color. It will be all shuffled and not combined together. Okay.
Sometimes we can group them like based on patient characteristic, not build a cluster like cancer here and not cancer here, and just cluster the genes and see
Yeah, you
gene
can do that.
expression.
You can do that. Yes. You
I
can
like
do
the
it
color.
all different ways. It just depends on how you interpret it and what you want to present.
Exactly.
So the next one is the principal component analysis. So the goal of PCA here is to transform the number of possible correlated variables into a smaller number of uncorrelated variables called principal components. So this is essentially for the purpose of high throughput data analysis. We perform this just mainly for dimension reduction and easy visualization. Okay, we don't really perform further statistical analysis using PCA, but it's good for visualization. And then a possibly smaller number of variables can be used for data reduction and visualization. And one, important mathematical property of all these principal components, they are orthogonal to each other, which is very nice because they are uncorrelated. So each one independently represents one portion of variation in your data. So the first principal component is the projection of the data into a single dimension that has as high a variance as possible. So that means it accounts for as much of the variability in the data as possible. So it's basically PCA is a decomposition of your data based on variance. And after that, you project it to that new coordinate so that you can reduce dimension. So then each succeeding component in turn has the highest variance possible under the constraint that it is orthogonal to the preceding component. So therefore, the principal components, they provide a view on the structure of the data that best explains its variance. This is especially useful for exploratory data analysis because once you have more than 3 dimensions, you will not be able to actually visualize it clearly, intuitively. So this is after we perform the principal component analysis, we can usually plot it's not necessary you have 10 principal components. I mean, if you have high dimensional data, you can usually ask the software to plot the top 10 and to see how we usually focus on the first 3 principal components to see if these 3, the first 3 principal components account for the most variance of the data. If it's the case, then we could kind of not really pay much attention to the rest of the principal components. Okay, so this one, you see the first principal component account for about 23%. The second one is about 18%. It's not bad. This one is not a very good decomposition in terms of PCA. Anyway, just a demonstration. I don't know. It got cut off. Anyway, this is how a graphic explanation of how principal component is constructed. But of course, in reality, when they are actually calculated a principal component, a procedure called singular value decomposition is used. It's like a matrix decomposition, so that you can actually calculate the PC1, PC2, and PC3, etc. So imagine if we have only 2 dimensions. Well, this will be an overkill for PCA, but just for demonstration. Okay, imagine you only have 2 dimensions, and all your data point falls into this like oval scale, oval shape. And to construct the first principal component, you basically want to draw a line here, and kind of rotate your line until you find a line that all the data point, the projection onto this, the data point projection onto this line, that account for the most variation of the data. Okay, this is when you fix this line, and this one. The direction, this is the direction of the first principal component. And then the second principal component will be easy. It's just orthogonal to your first principal component. Okay? And now we have the first 2 principal components. And to visualize the data, actually, is we rotate discard the old coordinate. We rotate this and form a new coordinate system. And the x-axis is the first principal component, the direction of the PC1, and the y-axis is the direction of the PC2. Okay? So imagine if you have a 3-dimension, it's similar thing. It's just make it to a new coordinate system. And then you can look at the data a different way. Okay? Just like you look at a person, like this angle, but for principal component, you look at it this way. Then you reduce it to a lower dimension. But lower dimension, there are many directions you can look at it. The direction that principal component analysis uses is a direction that account for the most variation, the first principal component. And the follow one will be orthogonal to the second most variation, and things like that. It doesn't change the data. It's just the way you look at the data at a different angle. Okay? It doesn't reduce any information carried by the data. As long as the first few principal components represent most of the variation in the data, I should say that. If you only account 1%, then we shouldn't use the principal component analysis. Okay. So this is a data example. It's a Colgate study for periodontitis data, a patient. So I ran this analysis. So it's just a demonstration. So this is microarray data. We have periodontitis data, patient, gingivitis, and healthy subject. So I kind of perform. There's actually 2 types of data. One is a gene expression, one is a methylation. But that's still based on the B-chip array, not the sequencing data. So the key comparison is that they want to compare gingivitis versus healthy control, because this process is reversible. So we want to identify a set of candidate biomarkers that are differentially expressed between the gingivitis and healthy control. Okay. And this is just a demonstration. I performed some analysis and I identified 55 differentially expressed probe set between the gingivitis and healthy. And then just as a demonstration, I plot the principal component analysis plot. The blue color is healthy control and the salmon color is gingivitis. As you can see, based on this 55 differentially expressed probe set, we could kind of see 2 clusters. And the ovals here, okay, I forgot this is the eclipse here is a 95% confidence interval for the. But anyway, this oval is not necessary. You don't need to plot this. I just added this. But the principal component analysis, you can see, by looking at data in this way, we sort of see 2 clusters, right? They separate them. And when you are doing gene expression analysis, I would recommend you to do PCA first after you perform some filtering, pre-processing of the data first, and look at your data to see if you can see any pattern. And then after you perform differential expression analysis, we do the PCA again to confirm whether we actually separate the data. Because this is actually does not make much sense because we already know they will separate the data, right? But when you're submitting to a manuscript, the reviewer, they always want to look at a nice picture, just to show, to demonstrate, we could separate the sample, and this is one part that you could present. And usually they will not ask any question if you present this. But for exploratory analysis, it's hard to see any pattern, and you present that part, it does not provide much information. Anyway. And then this is the PCA based on methylation data. So based on 78 differential methylated CpG sites, this we don't see very clear separation. But still, I mean, if you draw your line here, well, this area they kind of like mix together, but this area they are separate, right? At least we don't see the red dot here. That's a good thing. And if you look at the principal component, the first principal component only account for only about 11%. So it's not very representative. Also, the second component only 7.9. So I would say using PCA probably is not very useful for separating the sample because there are still almost 80% of the variation of the data not accounting for. Does it make sense?
Would you please go back to the first one as well? First one? The previous
22%,
22,
and 10. This is okay. But the second one, we lost a lot of information. Like 80% of the variation in the data is not presented here. So if we don't see separation here, it doesn't mean it does not work. It's just there are 80% of the variation, like all the information not really being explored by this plot. That's what I would like to say. Yeah, it doesn't mean it does not separate. It's just the PCA is not very useful. And there is another way. I believe you all heard about that. That's the multidimensional scaling, the MDS. So that one is also useful. So PCA, you can think of PCA as the simplest form of multidimensional scaling. PCA is not it's not an algorithm. PCA is actually a procedure. It's a mathematical procedure. It is not any algorithm. But multidimensional scaling is the method. It rescales the data and then apply PCA. Well, one type of MDS is like that. So this is a wild variation of multidimensional scaling method. And you can read more about this, but I will not cover it here. Just too complicated for this course. Well, anyway, that's all for today. I hope